Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore the surprising patterns that emerged when neural networks were scaled, the laws that link data, parameters, and compute, and why they reshaped the entire trajectory of modern AI.
It's truly one of the most fundamental shifts in the entire history of machine learning. For decades, if you wanted a better model, the focus was so heavily on architectural innovation.
The guiding principle was that you had to be clever.
Right,
Yeah.
Exactly. You had to invent a radically new loss function, or find a groundbreaking tweak to how you stack the layers, or a better way to initialize the weights. Anything to squeeze out that extra bit of performance.
Right, and the prevailing idea, the historical assumption, was that these performance improvements in neural networks would just eventually hit a ceiling.
They'd plateau.
Researchers really believed that if you just made a model larger, the marginal gains would diminish so quickly that it wasn't worth it. You'd hit a capacity wall.
And the only way past that wall was through these superior engineering ideas, not just brute force scale.
So they were all hunting for the perfect complex algorithm.
They were. Assuming that the simplicity of just scaling up resources would fail, people spent huge amounts of time hunting for those magic architectural tweaks. And those tweaks were often complicated, very model-specific.
But then came this realization, which was, it must have been shocking in its simplicity.
It really was. Instead of hitting a hard ceiling, performance just improved consistently, smoothly, and perhaps most importantly, predictably.
Predictably, just by adding more of the core resources.
Yes. And that consistent, predictable improvement across enormous scale led to the discovery and the formalization of these scaling laws.
They demonstrated that performance followed these clear mathematical relationships, specifically power law relationships.
Linking the model's test loss to those three critical resources: the number of parameters, the amount of data, and the total compute used.
To really frame this discussion, we should probably establish what we mean by performance.
That's a great point. The goal of training these large models, especially language models, is to minimize something called loss. You might see it written as L or epsilon.
Which is typically the cross-entropy loss, right? And for language models, it's measured in something called nats.
Correct. And loss, you can think of it as a measure of how poorly the model performs at its main task, which is predicting the next word or token in a sequence.
So a smaller loss value means the model is making better, more accurate predictions. It's performing better.
Exactly. So the scaling laws, they essentially provide a quantifiable metric for progress. They describe precisely how quickly this loss decreases as you increase your budget in one or all of those three resource dimensions.
And this shift, it moved the entire development process out of what felt like alchemy, trial and error.
And into what researchers now call principled design.
You've used an analogy before that I think is crucial here, that these relationships act as analogs of the ideal gas law in physics.
It's the best way to grasp the scope of this finding. Think about that law. PV equals nRT. It universally relates pressure, volume, and temperature, these macroscopic properties.
And it does that regardless of the microscopic details of the gas molecules. It doesn't matter if they're argon or oxygen.
Precisely. Scaling laws do the same thing for neural networks. They relate the macroscopic properties of a training run parameters, data, and compute to the resulting test loss.
And this relationship holds largely independent of the specific microscopic details, like which activation function you chose or how many attention heads you used in your transformer.
That universality is why it changed everything. It provided a stable, predictable framework for seeing into the future of a training run.
That sets the stage perfectly. Okay, so let's unpack the scientific framework, starting with the first pillar, the capacity of the system itself. Parameters, which we call N.
So parameters N are defined intuitively as the size or the capacity of the neural network.
It's the raw count of tunable weights and biases inside the model that the optimization process is trying to set correctly.
Right. We think of it as the model's ability to store information in complex patterns.
And crucially, the researchers who formalized these laws found that they got significantly cleaner scaling laws. if they systematically excluded certain parts of the network from that count. Why do that? If they're part of the model, why not count them?
That's a really sharp question, and it speaks to the nuance of what's actually driving the scaling behavior. They specifically excluded all vocabulary embeddings and positional embeddings from the parameter count n.
Okay, so why those specifically?
The reason is that these embedding matrices, which map individual tokens, like the word cat, or positions into vectors, are essentially just large lookup tables.
I see.
Their size is often dictated by external factors, like how big your vocabulary is, not the computational complexity of the internal learning process.
So the scaling laws are fundamentally about how the computation handles complexity, not how big the initial lookup dictionary is.
Exactly. The core scaling behavior, the power law, was found to be driven by the computational complexity living inside the main transformer blocks themselves.
So the layers, the width, the feed-forward dimensions.
That's right. Those are the parts performing the transformations, the comparisons, the heavy lifting of pattern recognition. By excluding the embeddings, they isolated the purest signal of scaling how loss decreases as the capacity for complex internal computation increases.
And what they found when they isolated n was the parameter power law. Performance improves as n increases, and this is quantified as a power law where the loss, L, scales inversely with n by a certain exponent.
Yes, alpha.
Okay.
And the practical effect of this is astonishingly steady. It's predictable. For typical language models, that exponent was found to be approximately 0.0076.
Now that number represents the rate of diminishing returns, right?
It does. Doubling the number of parameters yields a loss that is smaller by a constant factor, which is 2 to the power of negative alpha. That works out to about 0.95 for language models.
Okay, so let's make that concrete. If your cross-entropy loss was, say, 3.0, doubling the size of your model would get you down to roughly 2.85.
That's
My first reaction to that is, well, if that improvement is so small, a 5% reduction in loss for doubling the entire size and cost, why are companies spending millions, even billions, to chase that small gain? Is there a point where it just becomes financially irrational?
That is the critical financial and engineering question. The answer lies in two parts. First, those small fractional improvements in loss, they compound over multiple scaling steps.
Okay.
More importantly, those fractional improvements often translate into these nonlinear step function improvements in qualitative capabilities.
Like what?
Like the ability to reliably follow complex instructions or perform nuanced reasoning or write coherent long-form code. That 5% gain in loss might be the difference between a model that's a clever toy and one that is a deployable revenue-generating product.
And the second part?
The second part is the consistency. The curve shows no immediate hard ceiling. We're talking about 6, even 7 orders of magnitude in n, from tiny models to massive ones. And the curve just keeps smoothly dropping according to that predictable 0.95 factor.
That guarantee must be worth billions.
It is.
So why does this expressive power matter so much? What capacity are these vastly larger models gaining that the smaller ones just fundamentally miss?
The key is the ability to encode complexity, especially long-range dependencies in data like language. Think about a complex legal document or a long chapter in a book where a pronoun in the last sentence refers back to a specific person mentioned hundreds of words earlier.
Like trying to correctly parse a sentence where the subject and the verb are separated by an entire paragraph of subordinate clauses.
Exactly that. Smaller models, they simply lack the weight capacity, the information bandwidth, if you will, to consistently maintain and reference those distant connections.
And the evidence shows that as you scale up, they get better at this.
Steadily better, across the entire context length. For models trained on a context of, say, 20 or 24 tokens, the larger models are dramatically more effective at detecting these complex long-distance patterns compared to older architectures like LSTMs.
Which often saw their performance capabilities just fall off a cliff after 100 tokens or so.
Right. Scaling allowed the transformer architecture to really realize its full, long context potential.
This brings up a finding that is, well, it's truly counterintuitive to anyone who has worked in traditional engineering, this idea of architectural flexibility.
Yes.
I would expect that for a given parameter count, you'd need this hyper-specialized tuning, a perfect balance of depth versus width, or the exact right number of attention heads to get the best performance.
And that was one of the biggest shocks to the research community. The performance of these transformer models was found to be remarkably insensitive to the internal architectural shape.
As long as the total non-embedding parameter count, n was held fixed.
Correct. The exact ratio of depth, the number of layers to width, the dimension of the internal representation, it just didn't matter that much. You could swap a deep and narrow architecture for a wide and shallow one, and the performance varied by only a few percent over a wide range of shapes.
That completely flips the traditional engineering playbook on its head. It means raw, total size was far more important than the specific way you structured that size.
It reinforced the primacy of raw size over highly specialized design. And think about the engineering implication of that.
Oh.
If the performance is invariant to the shape, engineers gain immense flexibility. They are free to choose the architecture's shape deep and narrow versus wide and shallow based purely on hardware and deployment constraints, not performance concerns.
So a deep, narrow model might be better for memory efficiency.
And sequential processing, yes. While a wide, shallow model is typically better for parallel processing on things like GPUs.
The scaling laws confirm that you can choose based on efficiency because the performance will be predictable either way.
That's right. And that explains why so many massive models share such similar underlying structures. The focus shifted from structural genius to just maximizing these three pillars.
Okay, so we've established capacity, N.
Yeah.
Now moving to the second pillar, data, D. If parameters are the capacity of the warehouse, data is the inventory you fill it with.
It's the perfect analogy. If the model size is fixed, the performance you can extract is fundamentally capped by the data you feed it. Just as loss scales predictably with size n, it also scales predictably with dataset size d when the model is large but currently limited by data.
And this relationship also follows a power law, the data power law, L of D. Performance consistently improves with more training tokens.
Yes, scaled by an exponent, alpha d.
Okay.
And typically, the data power law exponent is slightly higher than the parameter exponent, alpha. It's around 0.095.
What does that hint at?
It hints that, generally speaking, adding more data yields a slightly faster marginal reduction in loss than adding more parameters. And that's a key insight for how you allocate your resources.
This brings us to the concept of the error landscape. Because N and D don't operate in a vacuum. Performance is determined by the relationship between them. You have to navigate this landscape efficiently.
That's right. And the landscape is really dominated by two saturation states. We can walk through those dual limitations.
Okay.
First, there's the data-limited regime.
This is where you're holding the size of the model fixed, but you're dramatically undersupplying it with data.
Let's try to make that concrete. Imagine you have a fixed, massive model capacity, a warehouse the size of a city, but you only show it a tiny repetitive data set, say a single textbook repeated thousands and thousands of times.
Okay.
Performance increases really rapidly at first as it learns the few patterns that are available, but then it quickly saturates to a level determined by its overwhelming capacity. It will perfectly memorize that textbook, but it won't generalize.
In this data-limited regime, the model is so huge that it quickly memorizes the limited data it has. So you need more data, more variety, to force it to generalize and keep improving on unseen test sets.
Yes, that's the correct way to think about it. You have all this capacity, but you lack inventory variety. The model's ceiling is imposed by the sparsity of the data.
Now, conversely, you have the model-limited regime. This is where you have a fixed data set, but you keep growing the model size. And
Right, so here you have a fixed inventory, maybe 100 terabytes of text, and you just keep building bigger and bigger warehouses to store it.
so what happens then?
Well, performance improves as the model grows, as it learns the intricacies and subtleties of that fixed data set, but it eventually reaches a saturation level dictated by the data itself.
So if you only have 100 images, building a model with 1 trillion parameters won't make it generalize any better.
It'll just memorize those 100 images in excruciating detail. You've exceeded the utility of your data supply. The ultimate performance ceiling is fixed by the dataset size, regardless of how big you make the model.
So the key to getting efficient high performance is finding that optimal balance on the error landscape. And that has huge practical trade-offs because data acquisition and cleaning is incredibly expensive.
Absolutely. The research provided a quantitative framework for this. It turns out that large models do require large data sets, but the optimal dataset size grows sublinearly with the model size. Specifically, D grows proportionally to n to the power of 0.74.
Sublinearly. Walk me through the practical implications of that 0.74 exponent. Does that mean if I double the model size, I need to less than double the amount of data to keep it optimally trained?
Precisely. If D scaled linearly with ENSO, an exponent of 1.0 doubling your model size would mean doubling your entire expensive data acquisition and storage budget.
But because the scaling is sublinear, you need significantly less data than a linear relationship would suggest to maximize the utility of that larger model.
Right. This efficiency helps guide resource allocation. It prevents you from wasting money training an enormous model on data that's too sparse for its size, or conversely, acquiring vast data sets for models that are too small to utilize their full informational capacity.
And that leads directly into the third pillar, compute, C. If parameters are capacity and data is inventory, compute is the engine. It's the energy that drives the whole process.
Compute, or C, is the total training computation used. It's estimated by combining the number of non-embedding parameters, N, the batch size, B, and the number of training steps, S. The common approximation is C is about 6 MBS.
Okay, why the factor of 6? That seems like a very specific detail.
It is, and it's important for understanding the sheer volume of work being done. The factor of 6 accounts for the primary operations required for one forward and one backward pass during training.
Okay.
You need computations for the forward pass, calculating the output, then the backward pass, calculating the gradient of the loss, and then the subsequent steps for updating the weights and biases based on those gradients.
So this calculation provides a standard unit, the total number of floating point operations, which allows you to compare different runs fairly.
Exactly. And just like the other two pillars, when this resource is optimally managed, performance follows a highly predictable compute law.
Right.
When compute is optimally allocated, what we call sum-in, the test loss follows a predictable power law, L of sum-in. What's truly remarkable is that this predictability holds true across an unbelievable 8 orders of magnitude of computation.
That is a staggering range, from a tiny training run that cost pocket change to runs that cost hundreds of millions of dollars, and the fundamental behavior stays consistent.
It does. And this predictability around compute leads to arguably the most important practical insight for the entire industry.
Which is?
The massive strategic shift from purely focusing on bigger models to prioritizing better trained models for a given budget.
This is the concept of optimal allocation. It sounds like the heart of modern LLM design.
It is. When organizations have a fixed compute budget, C, there's one single optimal configuration of N, model size, D, data size, and S steps that maximizes performance for that specific budget.
This was a revolution, wasn't it? Before, people often just maximized N and ran training until the money ran out.
That's right. And what happens if you don't hit that optimal configuration? Say I fix my compute budget and train a model that's just unnecessarily large.
You end up with what are called undertrained models that waste potential.
Exactly. If you use your fixed budget to train a model that is simply too big, you won't have enough steps, S, to train it to convergence.
So it will perform worse than an optimally sized, fully trained model that strategically used the entire budget on a smaller size, a larger data set, and more steps.
You are literally throwing money away. A smaller, fully converged model would beat it.
So using a fixed budget efficiently means you have to dynamically scale all 3 dimensions at the same time. This is the optimal scaling path.
It is a blueprint for minimizing waste and maximizing performance for every dollar spent. Compute-efficient training requires that model size, batch size, and the number of steps must grow proportionally to the compute budget according to specific power law exponents.
And the allocation is highly precise, right? I've seen these numbers. N scales proportionally to C to the 0.16, S scales to C to the 0.06, and D scales to C to the 0.54.
Yes.
Let's dissect those exponents for a moment. D, the data, scales the fastest, then N, the size, and S, the number of steps, scales the slowest. What does that hierarchy tell an engineer?
That hierarchy tells you precisely where to invest your next dollar of computation. If you have an optimally trained model and you double your compute budget, you shouldn't just run twice as many steps or make the model twice as large.
You should prioritize getting and using significantly more data.
Right. Then moderately increase the model size, N, and finally run only slightly more training steps, S. It indicates that data utilization is the most leveraged lever for marginal performance gain under an optimal compute budget.
And this disciplined, balanced approach became the absolute blueprint for modern LLM development.
It did.
We should also note the theoretical limit here. These smooth scaling laws, they're not predicted to hold forever, are they?
No, but the theoretical boundaries are astronomical. We're talking around 10 to the 12 parameters and 10 to the 12 tokens, a trillion of each.
And the exact numerical values for that ultimate boundary are highly uncertain.
Very uncertain. But the concept suggests there might be an eventual ceiling, but that ceiling is far, far beyond anything we are currently building today. For all intents and purposes, the scaling laws hold across the entire spectrum of current practice.
The consistent scaling of all three pillars is what turned these observations into such a useful framework. This predictability completely changed how these systems are researched and deployed.
Which brings us to our next point, scaling laws as a predictive roadmap.
Right. The fact that the error curves are smooth and predictable means this isn't just descriptive science looking back at what happened. It's anticipatory. It guides future decisions.
And here's where the financial consequence gets really interesting. The idea that you can accurately predict the performance of a massive, expensive model from cheap, small-scale experiments.
That ability has to fundamentally change the risk calculation for these massive projects.
It's the ultimate cost saver and risk mitigator. Researchers found it was feasible to accurately predict the performance of models costing tens of millions of dollars from fits derived from configurations that were, say, 116th the size and trained on 18th the data.
And they could do this with high accuracy relative errors, often under 5%.
That's incredible, isn't it? You can essentially build a high-fidelity map of the performance landscape without ever having to traverse the most expensive terrain.
How often are these predictions accurate at the extremes of that scale?
When the fit is good for high-fit tasks, where the goodness of fit metric R-squared is above 0.95 predictions of a model 10 times larger, were accurate to less than a 3% difference.
That high degree of accuracy makes scaling laws invaluable diagnostics in the early stages of development.
They are?
How exactly are they used as diagnostics in a practical engineering scenario?
Well, they allow researchers to determine which pre-training objective or which hyperparameter setting or even which data filtering technique will be optimal at scale before they commit massive resources.
So an example, imagine you're deciding between two different pre-training methods.
Let's say masked language modeling versus pointwise mutual information. You can train small-scale models on both objectives and fit the scaling law curve for each one.
Then you just extrapolate both curves out to your desired massive scale, say a 100 billion parameter model, and see which predicted curve lands lower on the loss landscape.
Precisely. And the research shows that when that predictive fit is high, the predicted performance gap between the two methods holds the same sign as the actual gap you'll observe at the large scale.
Which means you can confidently bet your $100 million compute budget on the objective that looked better in the small-scale test. It's model selection, optimized for maximum expense efficiency.
Exactly. So instead of betting everything on a hunch, the scaling laws provide a clear, data-driven forecast that allows organizations to plan compute acquisition, data collection, and model size years in advance.
That's why these laws serve as the industry roadmap. They are the primary driver behind the evolution of massive models like the GPT series.
They weren't built through blind optimism. They were built following a predictable power curve with high confidence in the eventual outcome. It's a fundamental physical law applied to information systems.
Now let's widen the lens a bit. Does this powerful concept only apply to the textual domain of large language models?
Not at all. And the generality of scaling is one of the most compelling aspects of the discovery. Similar power law patterns are found all over the place.
Like computer vision, acoustic models.
Even models for reinforcement learning or models for board games.
We've seen recent evidence of this extending into time series data with what they call large time series models, or LTMs.
That's right. Used for forecasting complex financial or environmental data. When you use transformer architectures for LTMs, they show clear power law scaling for loss as a function of parameters, data, and compute, mimicking language models almost perfectly.
And just like their language counterparts, their performance is also weakly sensitive to architectural details.
Yes, like the number of attention heads or the aspect ratio. This suggests that the underlying scaling mechanism is a function of the training dynamics on complex data and the geometry of the loss landscape itself, not just the unique structure of human language.
This is great for training, but training happens once. Inference, the actual use of the model in the real world, comprises the vast majority of industry expenditures over the life of the model. Scaling laws seem crucial for inference optimization too.
Absolutely. Optimization for inference is essential for cost management, particularly through techniques like pruning.
Which is where you remove non-essential weights to create a smaller, faster model that hopefully maintains its performance.
So you're intentionally shrinking the capacity in, and you want to understand how the performance degrades predictably to find the limit of how small you can go without sacrificing quality.
And that leads directly to the pruning scaling law.
Correct. Researchers use methods like iterative magnitude pruning, or IMP, where weights with the lowest magnitudes are iteratively removed and the model is retrained to recover performance.
And when you plot the resulting error against the remaining density, the fraction of weights left, You see a very predictable two-stage pattern.
It starts with a broad, flat, low-error plateau. On this plateau, performance remains very similar to the unpruned network.
Meaning you can remove a significant portion of the weights, often 50% or more, with almost no performance loss.
That's the region where you gain massive efficiency for free. But then, as you prune further, you hit a specific critical density threshold. Beyond that, the error curve transitions into a sudden, steep power law increase in error.
That's the exponential drop-off in quality, the signal that you've cut too deep. And that critical density threshold is the practical limit for deployment optimization.
It is, but the scaling laws here yielded an even deeper insight by linking pruning to the actual shape of the model.
They did. How so?
A key discovery was the existence of an architectural invariant, often denoted as mum-star, that describes the arrow-preserving interchangeability between depth, width, and pruning density.
An invariant is a concept that stays constant even as other factors change. How does this specific invariant translate into practical design for, say, a resource-constrained deployment?
It means that the overall computational complexity required to achieve a certain loss level is constant, regardless of how you distribute the weights, as long as they maintain this invariant relationship.
Give me an example.
A developer can choose between a model that is very dense but narrow, or a model that is very sparse but wide and deep, and achieve the exact same performance level.
So if my deployment environment has limited memory bandwidth but massive parallel compute, I might choose a wider, deeper, but highly sparse model.
Exactly. The sparsity makes it fit into the memory constraints, even though it might have more parameters overall. The invariant allows you to maintain the target performance while optimizing purely for the hardware resource that is your biggest constraint, whether that's memory, latency, or energy consumption.
It enables principled design for deployment. This all paints a picture of astounding predictability, but it's based entirely on empirical observation on curves derived from data.
Let's move beyond what happens to why it happens. What are the theoretical origins of this error?
The theoretical work attempts to move beyond just fitting curves to try and explain the fundamental sources of generalization error. They break down the total error into conceptual categories rooted in statistical learning theory.
Okay, so we have a few potential sources of error here. Let's start with the one that's been identified as the source of that persistent, smooth, predictable power law scaling: uncertainty error.
Uncertainty error is a fundamental error that results from the stochastic nature of data sampling. It's the error that arises because the model is trained on a finite, randomly drawn subset of all possible data.
So even if the training algorithm is perfect and the model is infinitely complex, different random draws of data will result in slightly different models, leading to persistent variation or uncertainty in the final performance. This uncertainty is the mechanism identified as the source of the predictable power law region of scaling. The marginal benefit of any additional data sample just diminishes asymptotically, hence the power law shape.
Okay, and what about the second major source, the one that causes performance to eventually stop improving, the hard limit or performance plateau we see when one resource is fixed?
That's the learning deficiency error. This is defined as the failure of the learning algorithm, the optimizer, to perfectly fit the true target function.
So even if you have infinite data and a capable model, the optimization process itself might fail to find the best solution.
Right, because, for example, the learning rate was wrong or the training stopped too early. This deficiency is the mechanism identified as the source of the eventual performance plateau, usually when the model is severely undertrained or the optimizer just stalls.
This quantitative framework is incredibly powerful, but as we move from prediction to deployment, it runs into real-world complexities. It relies entirely on minimizing a single aggregate metric, like loss or accuracy.
And that's the critical challenge, the critique of metrics and values pluralism. Scaling laws demand a single universal performance metric to function, but these metrics are often imperfect proxies for true model quality, especially when scaled up to encompass huge, diverse populations.
What's the problem with using a single aggregate loss metric when the models get so massive, trained on trillions of tokens?
Well, as models and datasets grow trained on nearly the entire accessible web, the number of impacted subgroups, dialects, and communities represented in the data increases dramatically.
And the composition of these massive datasets, often scraped from public internet sources, is never truly representative of everyone.
Not even close. Low literacy communities, those in low resource language areas, or those relying on mobile technology for internet access, may be systematically underrepresented or excluded entirely.
And these diverse subgroups likely have different and potentially conflicting notions of good performance for a given task. Optimizing for one group's safety might degrade performance for another's language style.
Exactly. The aggregate metric used for scaling laws, generalized loss, may systematically hide similar divergences in values and preferences. Algorithmic unfairness highlights systematic variation of performance across subgroups using a fixed metric.
But values pluralism takes it a step further.
It does. It suggests the very metrics needed to evaluate success may need to vary across subpopulations, because what constitutes a good answer in one cultural context might be inappropriate or misleading in another.
So the goal of optimizing for a single universal loss metric breaks down when there are conflicting values about what success even looks like.
Correct. And it means that even if a model perfectly follows the scaling law and achieves a record low loss, the practical benefit may not be distributed equally across all communities. The law describes the physics of improvement, but not the ethics or sociology of impact.
Furthermore, beyond these challenges, the sheer economics of scaling create other problems, namely concentration and cost.
The cost is staggering. We're talking hundreds of millions of dollars for a single optimal training run.
And that demanding computational cost concentrates R&D primarily in organizations with immense resources.
Which leads to what is sometimes called an algorithmic rut or stagnation. The industry largely converges on a single proven architectural path, the transformer, because all the software and accelerators are overwhelmingly optimized for it.
So trying to explore truly novel ideas becomes prohibitively costly and inefficient.
Right. And the financial cost also translates into high environmental costs and increased safety risks because testing itself becomes prohibitively expensive.
If testing a small model is expensive, verifying the safety and fairness of a trillion-parameter model that took 6 months to train is exponentially worse.
It is. It raises genuine safety and governance concerns.
So if the scaling laws themselves create these concentrations of power and metric-based blind spots, the ultimate radical goal for the next generation of AI must be to find a way to break them entirely.
That's the consensus among forward-looking researchers. The next frontier is to find ways to break the current scaling laws, to achieve high performance, ideally maximal theoretical performance, without continually scaling N, D, and C.
And this search leads into the highly theoretical and, well, somewhat conjectural territory of Nyquist learners.
This is a fascinating line of thought that draws inspiration from classical signal processing, specifically the Nyquist-Shannon sampling theorem,
which specifies the minimal sampling rate needed for the perfect, unambiguous reconstruction of a signal.
Right. Researchers hypothesize that an equivalent principle might apply to learning functions from data. The theory rests on what's called the band-limited hypothesis.
That natural data problems arise from spectrally limited or band-limited functions.
In simple terms, if the underlying function describing the targets associated with the data samples doesn't vary wildly over the data manifold, if the data is, in a sense, smooth, then theoretically, the true function should be perfectly reconstructible from a finite, non-infinite set of samples.
So if this hypothesis holds true for real-world data, then perfect reconstruction, or the elimination of the uncertainty error source, could theoretically be achieved from a finite Nyquist dataset, not an ever-growing one.
Correct. The neural sampling conjecture posits that if we use algorithms that are explicitly designed to limit the spectral bandwidth of the model, what they call Nyquist learners, then finite optimal data could suffice for a given task. This fundamentally changes the scaling landscape.
Because the power law linked to data uncertainty would be eliminated.
It would be. And if you eliminate the uncertainty error by acquiring the perfect finite Nyquist dataset, then the dominant constraint on performance shifts entirely.
From uncertainty, which is solved by endless scaling of data,
to realizability, which is solved by finding a better architecture. This means the focus would shift back to the clever architectural tweaks and structural innovations that were once dismissed when scaling proved to be the easiest path forward.
So the journey started with the realization that brute force scaling worked better than we thought. And now the future hinges on finding a way to make clever architecture work better than brute force.
It's the ultimate feedback loop in science. And if we manage to break the scaling laws and achieve maximal theoretical performance from finite optimal data, the fundamental question shifts from how big must the model be to progress for whom, given those inherent values tensions we discussed.
That's the challenge we will carry into the next generation of AI, a compelling and necessary challenge to end on.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.